There exists a star so vast, so unfathomably enormous, that it defies the limits of human imagination. A star whose sheer size makes our entire solar system look like a fragile bubble that could vanish inside its boundaries without a trace. This is VY Canis Majoris. To call it colossal would be an understatement. It is one of the largest stars ever observed in the universe. If our Sun, the mighty engine that sustains life on Earth and reigns as the ruler of our solar system, were set beside it, the Sun would seem like a glowing ember compared to a roaring cosmic wildfire. The phrase "bigger than our solar system" is not exaggeration or poetic imagery. It is a literal description of this star's scale. When we think of our solar system, we think of vastness. Earth feels incredibly far from the Sun at nearly 150 million kilometers away. And yet, even at that unimaginable distance, our planet basks in the Sun's heat and brilliance. Jupiter orbits far beyond that, its giant bulk circling nearly 800 million kilometers from the Sun, while Saturn stretches the boundary further still, at almost 1.5 billion kilometers. To picture all of these planets, moons and orbits contained within the burning, swollen body of a single star is almost impossible. And yet, VY Canis Majoris has grown to such a size that if it replaced our Sun, it would stretch so far outward that the orbits of Saturn, and perhaps even Uranus, would be swallowed whole within its fiery red atmosphere. Every planet we know, every world that orbits the Sun, would be engulfed in its immense radius. But the true weight of this fact isn't just in the numbers, it's in what it makes us feel. To know that such a star exists forces us to confront how small we truly are in the cosmic scheme of things. For all our science, technology, and exploration, humanity is but a tiny flicker under the shadow of something so overwhelmingly vast. And the most humbling thought of all is that VY Canis Majoris is just one star, tucked away in a galaxy of hundreds of billions, within a universe containing trillions more. Its existence is both awe-inspiring and terrifying, a reminder that the cosmos operates on a scale so enormous our minds can barely comprehend it. VY Canis Majoris is not just any star. It belongs to one of the rarest and most extreme categories in the universe, a red hypergiant. Unlike the stable, steady glow of our Sun, red hypergiants represent a stage of stellar life defined by instability, expansion, and imminent collapse. These stars are the titans of the cosmos, pushing the limits of what it means to be a star, and VY Canis Majoris stands among the most extraordinary examples ever observed. It resides in the constellation Canis Major, the Greater Dog, a region of the sky visible from Earth's southern hemisphere. To the naked eye, you wouldn't notice anything unusual about this point of light. It doesn't blaze in the sky as one might expect from such an immense object. Its brilliance is hidden, shrouded in dust and distance, making it appear dim and unassuming from Earth. But behind that veil lies one of the largest stars ever discovered, a stellar giant that defies our understanding of scale. Astronomers classify VY Canis Majoris as a red hypergiant because of its immense size, its cool surface temperature compared to stars like the Sun, and its stage in the stellar life cycle. Hypergiants are incredibly rare. Only a handful are known in the entire Milky Way. They live short, violent lives, burning through their nuclear fuel at a furious rate and shedding their outer layers through powerful stellar winds. VY Canis Majoris is the embodiment of this cosmic extravagance, massive, unstable, and destined for a spectacular end. What makes it even more fascinating is that it doesn't shine across the sky as a beacon of its enormity. Instead, much of its light is absorbed and scattered by the thick clouds of gas and dust it has already thrown off into space. To study it, astronomers must rely on powerful telescopes and specialized instruments to peer through its shroud and measure its true scale. When they did, they discovered something staggering, a star so big that the human mind struggles to process its immensity. It is, quite literally, a cosmic extreme, one of the largest single stars ever recorded, outshining nearly everything else in terms of volume and size. To call it one of the largest stars known is not a statement made lightly. It is a testament to how unusual VY Canis Majoris is, a rare jewel hidden in the night sky that represents the very edge of stellar possibility. VY Canis Majoris resides at an almost unfathomable distance from us, sitting about 3,900 light-years away in the Milky Way galaxy. To put that into perspective, a single light-year is nearly 6 trillion miles, or about 9.5 trillion kilometers. So when we talk about 3,900 light-years, we're describing a span of distance so great that numbers begin to lose their meaning. Even traveling at the speed of light, the fastest speed allowed by physics, it would take nearly 4 millennia to reach this star. For humanity, with our current technology, such a journey is not only impossible, but incomprehensibly far beyond reach. This staggering distance is why VY Canis Majoris appears faint to the naked eye, despite its true brilliance. If it were closer, it would blaze with a brilliance that would rival the most luminous stars in the sky. But instead, it remains a dim, veiled giant in the constellation Canis Major, visible only with assistance and careful observation. Its remoteness doesn't diminish its significance. In fact, it enhances the sense of awe. Even across thousands of light-years, its size and power remain detectable, allowing astronomers to measure its properties despite the vast gulf of space between us. Thinking about 3,900 light-years also places Earth in context. Our solar system, vast as it seems, is less than a grain of sand compared to the cosmic ocean. Light that left VY Canis Majoris before the construction of the pyramids in Egypt is only now arriving on Earth, which means when we look at it, we're actually seeing it as it was thousands of years ago, not as it is today. It's a glimpse into the past, a window into an earlier chapter of the universe's story. This distance underscores a strange truth. Even the most enormous stars can seem quiet and unremarkable in our night sky simply because of how far away they are. Yet, when studied, they reveal themselves as titanic forces shaping the galaxy. VY Canis Majoris is a distant neighbor, hidden within the crowded star fields of Canis Major, but its presence is a reminder that the Milky Way is filled with extremes, objects so massive and extraordinary that they redefine what we think is possible. The true wonder of VY Canis Majoris begins to unfold when we start comparing its size to things we can at least partially comprehend. Numbers alone, like its diameter being about 1,420 times that of our Sun, don't quite capture the reality. Our minds aren't built to fully visualize such scales, so it helps to place these figures into more relatable contexts, ones that draw connections between what we know and what this cosmic giant truly represents. Let's start with our Sun, the dominant body in our solar system. The Sun itself is already an incomprehensibly massive object. Its diameter is about 1.39 million kilometers, and it contains 99.8% of all the mass in our solar system. Everything, the planets, moons, asteroids, and comets combined, make up only a fraction of what the Sun holds. Yet, compared to VY Canis Majoris, the Sun shrinks into near insignificance. Multiply that 1.39 million kilometers by over 1,400, and you begin to glimpse the size of this hypergiant. VY Canis Majoris's diameter is estimated at nearly 2 billion kilometers. That is not a typo. 2 billion kilometers across, stretching wider than the orbits of many of the planets in our system. If VY Canis Majoris were placed at the center of our solar system, where our Sun is, its outer surface would reach beyond the orbit of Jupiter, which circles the Sun at about 778 million kilometers away. That alone is staggering enough. Imagine a star so immense that Jupiter, the largest planet in our solar system, would orbit inside it. But the expansion doesn't stop there. This star's surface would extend well into the orbit of Saturn, which lies at about 1.43 billion kilometers from the Sun. Depending on how astronomers measure the star's radius, since its outer edges are not sharp, but instead fuzzy, turbulent, and full of ejected material, it might even creep outward toward Uranus's orbital path at around 2.87 billion kilometers. Let's think about that more clearly. The Earth, circling at a comfortable 150 million kilometers from the Sun, would not even be a speck inside this star. Our entire orbit, everything that makes our existence possible, would be buried deep inside its blazing outer layers. Mars, Jupiter, Saturn, all engulfed. Every planet we know, every celestial body we can see with the naked eye, would vanish within this single star's titanic radius. The Kuiper Belt, where icy objects like Pluto orbit, might be the first region of our solar system that would remain outside its fiery surface. Another way to appreciate this vastness is by looking at distances between planets. The gap between Earth and the Sun is often considered unimaginably large, 150 million kilometers. Yet that entire span, the Earth's whole orbit, would be barely a fraction of VY Canis Majoris's radius. Think of it this way. Light takes about 8 minutes to travel from the Sun to Earth. If light had to cross VY Canis Majoris from one side to the other, it would take more than 6 hours. Imagine that, a beam of light, the fastest thing in the universe, needing an entire quarter of a day just to pass from one end of this star to the other. Compare that with the Sun, which light crosses in just a little over 4 seconds. Numbers still feel abstract, so let's make it more visceral. If the Sun were reduced to the size of a coin, a small round object in your palm, VY Canis Majoris, placed at the same scale, would balloon to the size of a massive Ferris wheel. Or to go even further, imagine placing a basketball in one hand and a pea in the other. The basketball represents VY Canis Majoris, while the pea is our Sun. That's the scale difference between the two. And all the planets you know, Earth included, would be nothing more than microscopic dust specks clinging invisibly to the pea. This comparison doesn't just tell us about size, it gives us a sense of power. A star of such immensity doesn't just dominate in volume, it dominates in influence. Its gravity, its winds, its radiation, all extend outward in colossal spheres of control, far greater than anything our Sun could produce. Its outer layers don't sit still, they churn and boil, expanding and contracting, throwing off material into space. The star is so big and unstable that measuring its exact size is itself a challenge, because unlike the Sun, which has a clear visible edge, VY Canis Majoris fades into its surrounding gas, making the boundary between star and space murky. This is why its size estimates vary, with some earlier measurements suggesting it could be even larger than the current widely accepted 1,420 solar diameters. But even if we take the conservative estimates, the conclusion doesn't change. VY Canis Majoris is so large, it makes our solar system look insignificant. It transforms our conception of what a star can be. The Sun, which we rely upon for all life, suddenly seems fragile and tiny. And when we realize that VY Canis Majoris is just one star, in one galaxy, among hundreds of billions of galaxies, the immensity of the cosmos becomes almost unbearable to contemplate. And yet, it's that very immensity that sparks our awe. To think that somewhere out there, across thousands of light years, lies a star so vast that it could erase our cosmic neighborhood in an instant. It's both terrifying and humbling. VY Canis Majoris is not just large, it is beyond large. It is the very embodiment of what it means to push human imagination past its limits. Trying to imagine the scale of VY Canis Majoris with numbers alone is like trying to imagine the weight of a mountain by counting grains of sand. Numbers help, yes, but they fail to stir the visceral sense of awe that comes when we truly feel the comparison. This is where analogies become powerful, when we take the incomprehensible and anchor it to something our minds can grasp. Let's begin with a simple but striking image. If VY Canis Majoris were the size of a basketball, our Sun would be a tiny pea sitting beside it. A basketball, with its solid textured surface, rests in your hands at about 24 centimeters across. Place a pea next to it, barely a centimeter in size, and you immediately feel the imbalance. One dominates, the other is almost laughably small. Now imagine that basketball not as an object you can hold, but as a blazing sphere of gas, so hot it glows red, radiating energy across the cosmos. The pea, which we revere as the life-giver of our solar system, becomes pitiful in comparison, reduced to a flicker of significance beside the hypergiant. That, in essence, is the size relationship between VY Canis Majoris and the Sun. But we can push the analogy further. Imagine standing on a football field. At one end, someone places a basketball representing VY Canis Majoris. At the other end, almost 100 yards away, you set down a pea to represent our Sun. The basketball would dominate the scene. Even from across the field, it would command your vision. The pea, by contrast, might be overlooked entirely, lost in the grass. This is the scale difference we're dealing with. A Sun that feels overwhelming and inescapable to us on Earth, reduced to insignificance when placed next to the red hypergiant. Another way to picture it is to think of a skyscraper and a small toy. Imagine a towering building in a city skyline, stretching 100 stories into the air, standing firm as a monument to human achievement. Now set a toy figurine at its base, barely noticeable, dwarfed by the sheer vertical dominance of the structure. That's the same level of absurdity in size difference. The toy isn't just smaller, it's practically irrelevant next to the building. Similarly, the Sun isn't just smaller than VY Canis Majoris, it's insignificant when the two are compared side by side. And then, consider this. If Earth itself were represented by a grain of sand in this analogy, it would be utterly invisible in the presence of the basketball-sized hypergiant. Even Jupiter, the largest planet in our solar system, would shrink into obscurity. When we think of Jupiter, we often marvel at its massiveness, at its great red spot, large enough to swallow Earth whole. But inside VY Canis Majoris, Jupiter becomes less than an afterthought. Let's stretch this idea into a more dramatic picture. Picture yourself standing on a beach. You scoop up a pea-sized Sun in your hand, staring at it as if it contains the power of all life, which in reality it does for us. Now you turn your head, and before you, rising out of the ocean, is a glowing red sphere the size of a house, a mountain, a world, a basketball that radiates with the fury of nuclear fire. That is the reality of VY Canis Majoris next to our Sun. It's so immense, so dominating, that any attempt to bring them into the same mental frame feels absurd. But what's even more profound about this analogy is not just the scale of the two objects, but what it does to our perspective. We live our lives under the light of the pea, depending on its warmth and stability for everything we know. Yet somewhere in the galaxy, the basketball burns, dwarfing our Sun and humbling us with the knowledge that our most powerful star is little more than a speck when compared with what else the cosmos has to offer. Even when stripped down into something as simple as a pea and a basketball, the scale doesn't lose its awe. In fact, it becomes more visceral, more tangible. We can hold these objects in our hands, see them side by side, and feel that rush of amazement as the incomprehensible suddenly gains form. The pea and the basketball are not just a teaching tool. They are a mirror reflecting the truth that the universe operates on scales so vast, it humbles even the brightest light we know. Brightness is one of those qualities that seems simple until you place it on a cosmic scale. When you step outside on a clear day and glance toward the Sun, if only briefly, you experience just how overwhelmingly powerful our own star is. Its light, though it streams across space from 150 million kilometers away, is blinding. It illuminates our entire planet, fuels photosynthesis in plants, drives our climate, and defines the rhythm of life itself. It feels impossible to imagine anything brighter. Yet VY Canis Majoris laughs at this assumption. This red hypergiant shines with a luminosity estimated at around 270,000 times greater than the Sun's. Let's pause for a moment and absorb that. 270,000. If you could somehow combine the light of 270,000 suns and place them together in the sky, that is the kind of brilliance VY Canis Majoris pours into the cosmos every second of its existence. And remember, this is despite the fact that it is nearly 3,900 light-years away from us. Its brightness must cross that immense gulf of space, diffusing along the way, and still astronomers can measure its staggering energy output. That alone should hint at its power. It outshines almost everything in its neighborhood. The source of this brightness lies in its sheer size. The Sun shines as it does because of nuclear fusion at its core, where hydrogen atoms fuse into helium and release energy. VY Canis Majoris is doing the same thing, but on a scale magnitudes greater. Its interior burns with such intensity that the outer layers swell outward into its massive radius, and though its surface is cooler than the Sun's, the sheer area of that surface more than makes up for the difference. Imagine lighting a single small candle. It produces light, but it doesn't brighten a room. Now imagine an entire football stadium filled with thousands upon thousands of candles burning at once. The individual flame of each candle might be weaker than a spotlight, but together, their collective glow dominates the entire environment. That's how VY Canis Majoris works. Its cooler surface does not hinder its brilliance. Instead, the unimaginable size of its radiating body amplifies its luminosity beyond comprehension. To understand this on a human level, let's translate that energy into a familiar framework. The Sun's total power output, its luminosity, is around 3.826 watts. That's 380,000 watts. Now multiply that by 270,000. You arrive at a figure so immense, it breaks the calculator of the human imagination. Over 1.02 1032 watts. That's a 1 followed by 32 zeros. To put it in perspective, all of human civilization today consumes about 18 terawatts of power. That's 18 trillion watts. VY Canis Majoris outputs 10,000 times more energy than the entire human race uses. Not in a year, not in a day, but in a single second. This is energy on a scale that dwarfs our comprehension. Every photon that strikes Earth, every ray of light that gives us warmth and life, is part of the Sun's emission. Yet, VY Canis Majoris sends out hundreds of thousands of times more light into its surroundings. If our Sun were replaced with VY Canis Majoris, Earth would be incinerated instantly, not just from heat, but from radiation that would utterly sterilize any form of matter resembling life. Even planets much farther out, like Neptune or Pluto, would find themselves basking in levels of radiation far too extreme to allow anything familiar to us to exist. Now let's play with a thought experiment. Imagine looking up at the night sky and seeing VY Canis Majoris positioned at the same distance as our Sun. The brilliance would not just light up the day, it would wash over everything with a red glow so blinding and so powerful that the distinction between day and night would disappear entirely. The Earth would never see darkness again. The light would be so overwhelming that our atmosphere itself would likely ignite into catastrophic storms of energy. This isn't simply brightness as we understand it, it's cosmic domination. But here's the irony. From Earth, VY Canis Majoris does not appear that bright to the naked eye. In fact, it's relatively obscure compared to some of the well-known stars like Sirius or Betelgeuse. That's because its light has to travel nearly 4,000 years to reach us, and along the way, much of it is absorbed and scattered by the interstellar dust surrounding the star. What we see is only a faint echo of its true brilliance. Astronomers, using infrared observations, can peer through this dust and get a clearer sense of its output, and it is through these instruments that we discover its staggering luminosity. Without that technology, VY Canis Majoris would remain hidden in plain sight, a titan lurking quietly in the heavens, disguised by its own shroud. It's also important to note that its brightness is not constant. Like many hypergiants, VY Canis Majoris is unstable. It swells, it contracts, it throws off massive amounts of material, and its luminosity shifts with these violent processes. At times in its life, it may have shone even brighter, perhaps nearing 1,000,000 times the sun's luminosity. That volatility is part of what makes studying it so fascinating. It isn't a static giant sitting quietly in the cosmos. It's a dynamic, roaring furnace on the brink of destruction, its brightness fluctuating like a dying flame in the wind. Only this flame is brighter than hundreds of thousands of suns combined. The brilliance of VY Canis Majoris also plays an important role in shaping its environment. That immense energy output drives stellar winds that push gas and dust outward, creating nebulae that can span light years across. It doesn't simply shine, it sculpts the cosmos around it, carving out spaces where new stars may one day form. In this way, its brightness is not just a measure of raw power, but of influence. Its glow reshapes the interstellar neighborhood, leaving behind a legacy that will persist long after the star itself has perished. Ultimately, when we talk about VY Canis Majoris shining 270,000 times brighter than our Sun, we're not just stacking one number against another. We're revealing a truth about extremes, that even our Sun, which feels eternal and all-powerful to us, is a modest star by the standards of the universe. VY Canis Majoris is a beacon of scale and energy that strips us of arrogance, reminding us that the cosmos is always capable of producing something greater, brighter, and more unimaginable than what we've seen before. When we turn from size and brightness to mass and density, VY Canis Majoris reveals another paradox of stellar existence. It is both staggeringly massive and, at the same time, extraordinarily thin and diffuse. At first glance, saying a star is 17 to 25 times the mass of our Sun might sound like it should be crushingly heavy and compact, almost like a scaled-up version of the Sun itself. But in the case of this red hypergiant, that assumption couldn't be further from reality. VY Canis Majoris spreads that mass over such an inconceivably large volume of space that it becomes one of the most ethereal and diffuse objects in the galaxy, almost like a cosmic ghost of a star, more air than matter, more emptiness than substance. Think of it like this. Our Sun has a radius of about 700,000 kilometers, while VY Canis Majoris extends out roughly 1,400 times farther. That expansion alone means its total volume is billions upon billions of times greater than the Sun's. And yet, the mass hasn't increased in the same proportion. With just a few dozen solar masses at most, it's as though VY Canis Majoris has inflated like an enormous balloon, stretching its stellar material so thin that it is on the verge of falling apart under its own instability. If you could somehow scoop up a chunk of its outer layers and hold it in your hands, it would be far less dense than air, so insubstantial that it would barely seem to exist at all. To put this in perspective with some numbers, the Sun's average density is about 1.4 grams per cubic centimeter, slightly denser than water. VY Canis Majoris, on the other hand, has an average density closer to a few 10,000ths of a gram per cubic centimeter. That's thinner than the air you're breathing right now. Imagine walking through a fog that seems thick, but is really just water vapor spread thinly across a large space. That's the kind of thinness we're talking about, except instead of water vapor, it's a massive shroud of plasma, hydrogen, and helium gas stretched across a span billions of kilometers wide. The paradox here is fascinating. Despite its low density, the star is still incredibly massive by any human standard. 17 to 25 solar masses is enough matter to build 17 to 25 suns, each capable of sustaining planetary systems of their own. In fact, if you compressed all that mass into a volume the size of the Earth, you'd create a black hole. Yet in VY Canis Majoris, That same mass is smeared out across a region larger than the orbit of Saturn. This is the great irony of hypergiants. They are massive enough to bend the rules of stellar physics, but too large and diffuse to maintain stability for long. This extreme combination of mass and thinness also explains why VY Canis Majoris is in such a precarious stage of its life. Stars like our Sun burn their hydrogen steadily, lasting billions of years. But massive stars burn their fuel far more quickly. In the case of VY Canis Majoris, its enormous size means its outer layers are unstable, constantly swelling, contracting, and shedding matter into space. Observations show colossal plumes of gas being ejected from the star, arcs of material larger than our entire solar system, drifting away into the void. These eruptions are evidence of the tug-of-war between gravity pulling inward and radiation pressure pushing outward. The balance is delicate, and it makes the star volatile, unpredictable, and fragile. One way to imagine this is by comparing the Sun and VY Canis Majoris to two different kinds of fires. The Sun is like a steady candle flame, bright, stable, and consistent. VY Canis Majoris, by contrast, is more like a massive bonfire. It blazes brilliantly, consuming vast amounts of fuel in a short time, and it flares and sputters, throwing out sparks and embers in every direction. The reason the bonfire doesn't last is the same reason VY Canis Majoris won't last long. It is burning through its fuel at a furious pace. Its incredible luminosity, hundreds of thousands of times brighter than the Sun, is powered by nuclear fusion happening at rates so extreme that the star is essentially tearing itself apart from the inside out. And this leads to another point about its density. Because its outer layers are so thin, the star's core bears much of the responsibility for holding the structure together. Deep inside, where pressures and temperatures soar into unimaginable extremes, nuclear reactions rage at a furious pace. The energy generated there is enough to push back against the pull of gravity, but it doesn't travel through solid matter like in the Sun. It moves through mostly empty space, colliding with sparse particles along the way. This means the outer layers are constantly in motion, rippling, bubbling, and throwing off matter, like a pot of water at full boil with no lid. If we were to place Earth inside VY Canis Majoris, not only would our planet be deep within the star's body, but we would be swimming in plasma, that is, on average, less dense than the air at sea level. This strange fact flips our everyday intuitions. We think of stars as solid, blazing balls of fire, but in reality, especially for hypergiants like VY Canis Majoris, they are more like vast, fragile clouds of gas loosely bound together by gravity, with a furious core trying to keep them from collapsing altogether. Another astonishing implication of its mass and density is the role it plays in the star's inevitable fate. The more massive a star is, the more dramatically it dies. For VY Canis Majoris, astronomers predict that its life will end in a cataclysmic supernova, or perhaps something even more exotic, like a hypernova, an explosion hundreds of times more powerful than a typical supernova. When that happens, the star's core will collapse under the weight of its own gravity, possibly forming a neutron star or even a black hole, while the outer layers are blasted into space at tremendous speeds. All of this chaos is already written into the balance of its mass and density. The star is so bloated, so unstable, that it cannot possibly last much longer on cosmic timescales. In short, the paradox of VY Canis Majoris lies in its duality. It is one of the most massive stars in existence, yet its vast bulk is spread so thin that it behaves more like a gigantic cloud than a star as we imagine them. Its density is lower than air, yet it contains enough matter to collapse into one of the most extreme remnants in the universe. Its mass gives it power, but its diffuse structure makes it fragile. That balance is temporary, fleeting, and ultimately destined to end in one of the most violent deaths a star can experience. Despite being one of the largest stars ever discovered, VY Canis Majoris isn't scorching hot like many people imagine stars should be. In fact, compared to our Sun, it's relatively cool. Its surface temperature is measured at around 3,500 Kelvin, much lower than the Sun's surface, which burns at about 5,778 Kelvin. Now, 3,500 Kelvin might still sound unimaginably hot, but in the cosmic scale of stars, that actually places VY Canis Majoris among the cooler giants. This is why astronomers classify it as a red hypergiant. The color of a star tells us a lot about its temperature, and in this case, the reddish hue of VY Canis Majoris is a direct reflection of its relatively cooler outer layers. When you think of the Sun's blazing white-yellow light, you're seeing the effect of higher surface temperatures. Hotter stars than the Sun, such as blue giants, can reach tens of thousands of Kelvin and shine with piercing blue-white light. But VY Canis Majoris, despite being hundreds of thousands of times more luminous, radiates a softer, redder glow because of its cooler surface. This creates a fascinating contrast. It's not the heat at its surface that makes it one of the brightest stars, but the sheer immensity of its size. Imagine this. The Sun is like a furnace burning intensely hot, compact and steady, while VY Canis Majoris is more like an enormous bonfire. Its flames don't need to be as hot individually because the fire itself covers such a colossal area. The star's enormous surface area compensates for the cooler temperature, radiating vast amounts of energy into space. Even though each square meter of VY Canis Majoris emits less heat than the Sun's surface, it has such an unimaginably gigantic surface that the total energy it pours into the cosmos is hundreds of thousands of times greater. This cooler temperature also explains why the star appears red. In physics, the spectrum of light emitted by an object depends on its temperature. A star like the Sun, at nearly 6,000 Kelvin, peaks in the visible yellow-white range, while cooler stars shift toward the orange and red end of the spectrum. At 3,500 Kelvin, VY Canis Majoris radiates most of its energy in the red and infrared part of the spectrum. So, if you could travel close enough to this star and see it with your own eyes, you would not see the blinding white glare of a sun-like star, but a vast, deep red glowing sphere dominating the sky, looking more like a cosmic ember than a flame. This cooler surface also suggests something important about VY Canis Majoris's life cycle. It's nearing the end of its stellar journey. Stars expand and cool as they age, swelling into supergiants when they've burned through most of their hydrogen fuel. That's exactly what we're witnessing with VY Canis Majoris. Its low temperature and immense size are signals that it's already left behind the stable, middle-aged phase of stellar life and has entered a volatile, unstable chapter. The outer layers of the star are puffed up and tenuous, drifting away into space in giant stellar winds. In fact, VY Canis Majoris is losing mass at an extraordinary rate, shedding material that forms a vast, dusty nebula around it. Another intriguing aspect is how this cooler temperature affects its structure. The Sun's high surface temperature means it is tightly bound, compact, and relatively stable. But VY Canis Majoris, with its cooler outer layers, has a much more diffuse and fragile atmosphere. Imagine the difference between a tightly packed ball of steel and a balloon filled with smoke. The balloon may look large, but it's fragile, unstable, and constantly changing shape. VY Canis Majoris is like that balloon. Its outer layers are so expanded and so cool that they're barely held together by gravity, and they constantly shift and pulse outward into space. This is also why its future is so precarious. A cooler, puffed-up surface means instability, and instability in a massive star is a recipe for a violent ending. The lower temperature suggests that VY Canis Majoris is already in the red hypergiant phase, one of the final steps before a catastrophic supernova or even a direct collapse into a black hole. Essentially, the coolness of its surface is the star's way of telling us it's running out of fuel and nearing its grand finale. If you picture standing on a hypothetical planet Orbiting near VY Canis Majoris, though realistically no solid planet could survive that environment, the sight would be utterly alien. The star would fill most of the sky, a dark, brooding red presence radiating a strange heat. Not the searing, blinding light of the sun, but a deeper warmth that seeps everywhere. The sky around you would glow crimson, and shadows would stretch in eerie ways under its dim but massive influence. It would feel as if you were living under a permanent sunset, the kind that never ends, stretching across the entire sky. Interestingly, the relatively cooler temperature also explains why VY Canis Majoris is surrounded by dust and molecular clouds. Cooler stars allow heavier elements and compounds to condense in their outflows, creating dusty shells and nebulae. The heat from a hotter star would simply vaporize these materials, preventing them from coalescing. But in the case of VY Canis Majoris, the cooler outer layers create the perfect environment for dust grains to form. This dusty envelope obscures parts of the star from our view, which is why images of VY Canis Majoris often show it as a dim, hazy object rather than the blindingly bright beacon you might expect. So while 3,500 Kelvin may seem modest compared to other stars, it's actually the perfect number to tell us about the star's condition, history, and fate. That relatively low surface temperature is the fingerprint of a dying giant, a star that has lived a life of extreme intensity, burning through its fuel much faster than our sun ever could, and now entering its final unstable act. It's a reminder that size doesn't always equal heat, and that the universe's most powerful phenomena often hide behind quiet, deceptive numbers. The temperature of VY Canis Majoris paints a picture of a star that is both majestic and doomed. It glows like a massive ember in the night, dimmer in hue but far grander in scale, a star whose cooling surface signals that it's nearing the end of its existence. And when that ember finally goes out, the resulting explosion will be so spectacular that it could briefly outshine entire galaxies, scattering the elements for new stars, planets, and perhaps even life to form elsewhere in the cosmos. VY Canis Majoris is not just a star. It is a cosmic elder, a giant burning in the twilight of its existence. To understand where it stands in its journey, we need to look at the grand cycle of stellar life. Stars, like living beings, are born, they evolve, and eventually they die. Their fates are written in their masses, and for a star as immense as VY Canis Majoris, the script is particularly dramatic, filled with fiery transformations and violent endings. This red hypergiant began its story, like all stars, inside a vast molecular cloud of gas and dust billions of years ago. Gravity pulled material together until hydrogen atoms were pressed so tightly that nuclear fusion ignited. In this first stage of life, it would have burned as a massive, bright, hot blue star, radiating far more intensely than our sun could ever dream of. For millions of years, it lived in this main sequence phase, steadily fusing hydrogen into helium in its core. But unlike smaller stars, which can linger in this stage for billions of years, massive stars like VY Canis Majoris burn through their fuel incredibly quickly. Their brilliance comes at the cost of longevity, trading stability for sheer energy output. Once its core hydrogen began to run out, its internal balance collapsed. The outward pressure from fusion, which had been resisting gravity all this time, faltered. Gravity squeezed the core, increasing the pressure and heat until helium began to fuse into carbon and oxygen. At this point, the star's outer layers expanded enormously, ballooning outward to create the red hypergiant we see today. Its surface cooled as it swelled, giving it that deep reddish glow, but its sheer scale became staggering, over 1,000 times the radius of our sun. Right now, VY Canis Majoris is in this late evolutionary stage, a swollen giant at the edge of stability. Its core is a furnace where heavier and heavier elements are being forged in a process called nucleosynthesis. After helium, it will move on to fusing carbon, then neon, magnesium, oxygen, and eventually silicon, producing ever heavier elements. But here lies a cosmic inevitability. Once iron begins to form in the core, fusion no longer produces energy, it consumes it. At that point, no matter how immense the star, gravity wins. That is the destiny awaiting VY Canis Majoris. At present, it is already unstable, shedding enormous amounts of mass through stellar winds, throwing material into space at thousands of kilometers per second. These eruptions sculpt the dusty nebula surrounding it, a visible reminder that the star is tearing itself apart as it nears the end. Astronomers suspect that this furious mass loss means the star could collapse sooner rather than later, astronomically speaking. The final stage will come when the core reaches the iron limit. Fusion will cease, and in an instant, the delicate balance that has kept the star alive will shatter. Gravity will crush the core inward in a catastrophic collapse, and the outer layers will rebound outward in a supernova explosion of unimaginable force. If VY Canis Majoris detonates as a supernova, it will briefly outshine entire galaxies, releasing more energy in seconds than the Sun will emit over its entire lifetime. But even this might not be the full story. Because of its enormous mass, many astronomers believe that the explosion may be followed by the formation of either a neutron star or, more likely, a black hole. Imagine a star so large that even in death, it might create an object from which not even light can escape. The stellar life cycle of VY Canis Majoris is not just a scientific tale. It's a story of cosmic impermanence, a reminder that nothing lasts forever, not even stars. Our Sun will one day swell into a red giant and gently shed its outer layers, leaving behind a white dwarf, a quiet ember of what it once was. But VY Canis Majoris is destined for a far more violent end. Its life is brief but brilliant, and its death will echo across the galaxy. What makes this moment in its life so fascinating is that we are witnessing it in its twilight, a rare chance to observe a red hypergiant at the brink of collapse. Out of the hundreds of billions of stars in the Milky Way, only a handful are in this fleeting phase. When we look at VY Canis Majoris, we are essentially staring at a countdown clock, though we cannot read the exact time left. It might explode in the next 100,000 years, or it could already have done so, with the light of its death still traveling toward us across the gulf of 3,900 light-years. To reflect on its life cycle is to glimpse the incredible variety of stellar fates. A small star might quietly fade into obscurity, but a titan like this leaves behind fireworks that reshape galaxies, forging heavy elements in its violent death. The calcium in our bones, the iron in our blood, even the gold in our jewelry, all these elements were born in stars that ended their lives in ways similar to the destiny awaiting VY Canis Majoris. Its story is not just its own, but part of ours too, for without stars like it, life as we know it would not exist. When we look at VY Canis Majoris, one of the most mind-bending aspects of this colossal star is not just its sheer size, its relatively cool temperature, or even its brightness, but the fact that its destiny is written in fire. A star of this magnitude cannot simply fade away quietly like our Sun will one day do, drifting into a gentle white dwarf state. Instead, its fate is nothing short of catastrophic. It is a ticking cosmic time bomb, destined to end its life in one of the most violent explosions in the universe, a supernova. Now, to understand why, we have to remind ourselves of what powers a star. For most of its life, a star survives through a delicate balance between gravity, which wants to collapse the star inward, and fusion, which pushes outward. In the core of a star like our Sun, hydrogen atoms fuse into helium, releasing energy that fights back against gravity. But VY Canis Majoris is no ordinary star. It is a red hypergiant, a star that has already burned through much of its hydrogen fuel. In fact, at its size and stage, it has moved far beyond the hydrogen burning phase and is now fusing heavier elements, helium, carbon, oxygen, silicon, in successive layers within its vast, unstable core. This is where the story becomes tragic, yet spectacular. As VY Canis Majoris cycles through these heavier elements, it's walking down a one-way road. With each successive fusion stage, the star produces less energy relative to the gravitational pressure trying to crush it. The last element it will ever fuse is iron. Why? Because iron does not release energy when it fuses. It actually absorbs energy. Once the core begins to fill with iron, the delicate balancing act that has kept the star alive for millions of years collapses in an instant. Gravity finally wins. Imagine this. The star's core, unable to resist its own weight, collapses at a speed approaching a quarter of the speed of light. We're talking thousands of kilometers per second. This catastrophic implosion compresses matter so tightly that protons and electrons are smashed together into neutrons. The collapse happens in milliseconds, and when it reaches the breaking point, the core rebounds violently. That rebound sends shockwaves tearing through the outer layers of the star, unleashing a detonation that outshines entire galaxies for weeks or even months. That is the death of VY Canis Majoris, a hypergiant gone supernova. If and when this happens, the explosion will be visible across the Milky Way. Even from Earth, some 3,900 light-years away, it could rival the brightness of the full moon in our sky, casting shadows at night and remaining visible even in daylight. That might sound terrifyingly close, but in astronomical terms, it's far enough away that we would not be in danger of physical harm. The radiation released would be immense, but distance shields us. Instead, we would bear witness to one of the greatest spectacles the cosmos has to offer: the birth of a supernova remnant, a brilliant nebula of glowing gas and dust expanding outward into interstellar space. But the story doesn't end there. A supernova is not just an ending, it's also a beginning. Such explosions are cosmic alchemists. They forge heavy elements, iron, gold, uranium, and all the metals we know, elements that cannot be formed in normal stellar fusion. These are hurled into the galaxy, enriching the interstellar medium and eventually seeding new stars, planets, and perhaps even life. In a way, we are all children of stars that died in similar cataclysms billions of years ago. Without stars, like VY Canis Majoris going supernova, Earth itself would not exist, nor would the atoms in your body. Its death ensures the continuation of cosmic evolution. Now, there's another layer of mystery here. Not every hypergiant ends its life in a neat textbook supernova. Some stars this massive can go out in stranger, even more violent ways. VY Canis Majoris could, for instance, collapse directly into a black hole after its explosion, or in some scenarios, without even an obvious explosion at all, what astronomers call a failed supernova. In that case, the star would simply wink out of existence, its outer layers swallowed by its collapsing core, leaving behind an invisible but immensely powerful black hole. This is why astronomers keep such a close eye on stars like VY Canis Majoris. Studying them allows us to probe the ultimate limits of stellar physics. What happens when stars reach sizes and masses beyond what we thought possible? Its death, whenever it comes, will not only be awe-inspiring, but also deeply informative. It will give us front-row data about the processes that shape galaxies, enrich the universe with heavy elements, and trigger the births of new star systems. So, while we can marvel at VY Canis Majoris today for its unbelievable size and luminosity, we also know that one day, tomorrow, 10,000 years from now, or perhaps even 1,000,000, it will meet its fate in a cosmic detonation so powerful that it will briefly outshine nearly everything else in the galaxy. The death of this star will be written across the sky, a glowing reminder of how even the mightiest giants must eventually fall, and how, through their fall, they breathe new life into the universe. VY Canis Majoris is not just remarkable because of its sheer size, brightness, and potential future explosion. It is also extraordinary in the way it is actively dismantling itself. This star is in the late stages of its life, and with that stage comes instability. One of the most dramatic processes at play is its massive and continuous loss of material through powerful stellar winds and eruptions, phenomena that shape not only the star itself, but also the surrounding space. These winds are unlike anything we can truly imagine on Earth. They are not the gentle breezes we know, nor even the violent storms of our planet. Instead, they are vast outflows of gas and plasma, moving at speeds of tens of kilometers per second, powerful enough to eject entire solar masses of material into the surrounding interstellar medium over thousands of years. For a star like VY Canis Majoris, this mass loss is not a side effect. It is one of its defining features. Because it is so large and extended, its outer layers are only weakly bound by gravity. Imagine a balloon stretched thin, where even a small puncture can release a massive amount of air. Similarly, the loosely held gases in VY Canis Majoris's outer envelope are easily pushed away by the combination of radiation pressure, turbulence, and instability. The star is essentially blowing itself apart, shedding layer after layer in a process that will only accelerate as it nears its ultimate end. The numbers involved are staggering. Astronomers estimate that VY Canis Majoris loses mass at a rate of about 1/1,000,000th of a solar mass each year. At first glance, this may not sound like much, but consider that a solar mass is equivalent to the entire mass of our Sun. This means that every year, VY Canis Majoris throws off material equivalent to several Earths into space. Over the course of tens of thousands of years, this mass loss adds up to a significant fraction of the star's total weight, gradually stripping away its outer layers and feeding the surrounding nebula. The winds are not uniform or gentle either. VY Canis Majoris has been observed to eject massive clumps of gas, creating asymmetric and chaotic structures in its surroundings. Rather than a neat, spherical shell, the material around the star looks more like a patchwork of arcs, knots, and clouds. These arcs are evidence of episodic outbursts, times when the star underwent particularly violent shedding events that blasted huge portions of its outer layers into space. Some of these arcs may be only a few hundred years old, meaning that humans, if they had been watching through telescopes back then, might have witnessed dramatic changes in the appearance of the star. What drives this immense mass loss? Part of the answer lies in the interplay of gravity and radiation. The star's enormous luminosity, hundreds of thousands of times brighter than the Sun, creates such intense radiation pressure that it physically pushes on the atoms and molecules in its outer atmosphere, accelerating them outward. Meanwhile, convection currents deep within the star churn its material, bringing heat and energy to the surface in turbulent waves. When these forces combine, they create instability that helps eject matter. In addition, as the star cools on its surface, molecules and dust grains begin to form in its outer atmosphere. These dust grains absorb starlight and are pushed outward like sails catching a wind, dragging the gas with them in a powerful outflow. The result of all this is that VY Canis Majoris is surrounded by an extended and complex nebula, a visible testament to its slow unraveling. Observations with advanced telescopes have revealed this nebula stretching across multiple light years, filled with intricate filaments and arcs of dust and gas. It is not a static structure either. Over time, the nebula evolves as fresh material is expelled, and older clumps drift farther into space. One day, when the star finally explodes as a supernova, this pre-existing nebula will serve as a canvas for the explosion's light and shock waves, creating an even more spectacular display as the two interact. For astronomers, the mass loss of VY Canis Majoris is not just fascinating to watch, it also provides critical clues about how stars like this live and die. Massive stars are notoriously difficult to model because they are rare, short-lived, and unstable. But by studying the nebula and the mass loss patterns of VY Canis Majoris, scientists can piece together what happens in the final stages of a hypergiant's life. These insights help us understand how much material such stars contribute to the galaxy. After all, the elements being ejected into space, carbon, oxygen, silicon, and more, will one day mix with interstellar clouds, helping to form new stars, planets, and potentially even the building blocks of life. The sheer scale of what is happening is almost beyond comprehension. If we could somehow stand at a safe distance and watch VY Canis Majoris, we would see not a single star, but a massive, shifting storm of glowing gas and dust, constantly changing as new waves of material pour outward. It would look less like a star and more like a fiery, living thing slowly dissolving into the cosmos. Its winds would be vast beyond imagining. Winds that could swallow solar systems, winds that carry the seeds of future worlds. What makes it even more awe-inspiring is the inevitability of it all. VY Canis Majoris is doomed to lose mass until it no longer resembles the giant it once was, setting the stage for its final supernova. The mass loss and stellar winds are not just random events. They are the signature of a star in the act of transformation, one whose death throes are already reshaping the space around it. In time, long after the star itself has vanished, its winds and nebula will remain as a reminder of its presence, an echo of one of the largest stars the universe has ever allowed us to see. VY Canis Majoris has not always been the celebrity of the cosmos that it is today. Its story stretches back centuries, woven into the history of astronomy itself, beginning as a faint entry in the observational logs of early skywatchers and transforming over time into one of the most closely studied stellar giants of the modern era. Long before powerful telescopes or digital detectors, observers charted the night sky with the naked eye, noting patterns and strange points of light that stood out against the starry canvas. Within the sprawling constellation of Canis Major, the Greater Dog, they recorded many stars, and among them was VY Canis Majoris, though in those times it was faint, red, and seemingly insignificant compared to the dazzling brilliance of Sirius, the brightest star in the night sky that dominates the same constellation. The earliest catalogued reference to VY Canis Majoris dates back to the 19th century. In 1801, the German astronomer Jérôme Lalande compiled observations of faint stars and listed VY Canis Majoris as a relatively dim object with little to distinguish it beyond its ruddy glow. To the observers of the time, there was nothing to suggest that this was anything extraordinary, let alone one of the largest known stars in the universe. It was faint to the eye, hovering near the edge of visibility without a telescope, and many assumed it was just another cool red star among countless others in the Milky Way. But as technology advanced, so too did astronomers' ability to unravel its secrets. By the mid-19th century, VY Canis Majoris began to attract more attention because it behaved oddly compared to other stars. Careful observers noted that it was not steady in brightness, but rather variable, sometimes appearing brighter and sometimes dimmer. In the mid-1800s, astronomers began classifying it as a semi-regular variable star, and this caught interest because such variability hinted at something unstable in its very nature. This was a clue that its story was not ordinary. Large stars often pulse, shedding material and fluctuating as they near the end of their lifespans, and VY Canis Majoris was already showing these telltale signs. The 20th century brought a dramatic shift in how the star was understood. With the advent of spectroscopic studies, astronomers could analyze the light from VY Canis Majoris and decipher the chemical composition and temperature of its outer layers. Its spectrum revealed deep absorption features and emission lines associated with hydrogen and other elements, which were evidence of powerful stellar winds and ongoing mass loss. This was not a stable star quietly burning away in its middle age. It was a dying giant, throwing off vast quantities of material into space. The star that had once been overlooked as a faint red speck was now recognized as an object of immense astrophysical interest. In the 1930s and 1940s, more sophisticated studies cemented the view that VY Canis Majoris was no ordinary red star. Photographic plates revealed that the space around it was shrouded in nebulosity, faint clouds of dust and gas likely expelled by the star itself. Astronomers began to realize that this was not only one of the most luminous stars known, but also one of the most massive in terms of material ejected into its surroundings. Observations suggested that the star was surrounded by arcs, knots, and shells of material. Clues that it had undergone repeated episodes of violent outbursts in the relatively recent past. The real turning point in its recognition as a record-breaking star came in the late 20th and early 21st centuries, when new instruments allowed for more precise measurements of its size and distance. Infrared astronomy was particularly crucial, since the star is heavily obscured by the dust it has ejected. In visible light, much of its brilliance is dimmed, but in the infrared, astronomers could peer through the dust and measure its true output. Observations from telescopes, such as the Hubble Space Telescope and ground-based observatories equipped with adaptive optics, revealed the intricate structures surrounding the star, confirming that it had been shedding material at astonishing rates. By the early 2000s, astronomers began to estimate its radius, and the numbers were staggering. Depending on which measurements were used, it appeared that VY Canis Majoris could be nearly 1,500 to 2,000 times the size of the Sun. This made it one of the largest known stars by radius. If placed at the center of our solar system, its outer layers would engulf the orbit of Jupiter, and possibly even Saturn, depending on the interpretation of data. These revelations propelled VY Canis Majoris into the spotlight, making it a headline-grabbing, largest star in the universe in popular science discussions. Yet the story of its discovery and study is not one of instant recognition, but of gradual revelation. For centuries, it was just a faint, overlooked point in the sky. Only with careful observation, advancing technology, and the persistence of astronomers did its true nature begin to emerge. Each era of discovery added new layers to its identity, from an unremarkable catalogue entry to a variable star, from a variable to a red hypergiant, and from a hypergiant to one of the largest and most extraordinary stars known to science. Today, VY Canis Majoris is no longer thought of as obscure, but as a symbol of the extremes of stellar evolution. Its discovery history is a reminder of how our understanding of the cosmos evolves with time. What once seemed mundane can later be revealed as magnificent, depending not only on what we see, but on how we look. The faint dot in Lalande's 19th century catalogue has grown into an icon of astrophysics, a star whose discovery story mirrors the story of astronomy itself, a journey from the limits of human sight to the limits of human imagination, aided by ever more powerful tools of observation. Observing a star like VY Canis Majoris is a challenge unlike almost any other in astronomy. At first glance, one might assume that because it is so massive, so bright, and so large, studying it should be relatively straightforward. After all, when something is over 1,000 times wider than the Sun and hundreds of thousands of times brighter, shouldn't it practically announce itself to our telescopes? Yet the reality is far more complicated. The very nature of this star, its distance, its environment, and even the limitations of human technology make it one of the most difficult stellar objects to measure and understand with precision. One of the most immediate challenges comes from the fact that VY Canis Majoris is not a neat, tidy star with a clearly defined edge. Stars like our Sun have relatively smooth atmospheres that allow scientists to measure their diameter, temperature, and brightness with fairly good accuracy. But hypergiants, especially red hypergiants like VY Canis Majoris, are not so simple. They are turbulent, unstable, and chaotic. Their surfaces are not flat or calm, but roiling with massive convective currents that create bright and dark patches across their surface. These convective cells can be so large that each one might span the size of our entire Sun. When astronomers attempt to measure the size of VY Canis Majoris, these irregularities distort the readings, leading to enormous uncertainties. Depending on how and when the measurement is taken, its estimated radius has been placed anywhere between 1,400 and 2,000 times that of the Sun, showing just how difficult it is to pin down. Another problem arises from the dense clouds of material surrounding it. Over the course of its life, VY Canis Majoris has shed vast amounts of gas and dust into the surrounding space, creating a complex nebula that partially obscures it from our view. This nebula is not uniform either. It is full of clumps, arcs, and knots of material that scatter and absorb light in unpredictable ways. When telescopes try to measure the brightness of the star itself, the data is often contaminated by this surrounding cloud. Some wavelengths of light pass through the dust fairly easily, while others are blocked or scattered, creating a distorted picture. This makes it extraordinarily difficult to know how much light is actually coming directly from the star versus how much is being altered by its dusty shroud. Distance is another major obstacle. VY Canis Majoris is around 3,900 light-years away from Earth, which might not sound like much compared to the overall size of the galaxy, but in terms of observational precision, it makes a big difference. Even for modern telescopes, resolving details of an object so far away is like trying to measure the size of a grain of sand from hundreds of kilometers off. Small uncertainties in distance measurements can cascade into massive errors in calculating the star's size and brightness. For example, if the star is slightly closer than expected, it would mean that its actual size and luminosity are smaller than current estimates suggest. Conversely, if it is farther away, its true size could be even larger than the already mind-boggling numbers astronomers use. Another complication is variability. VY Canis Majoris does not shine with a steady light like a lighthouse beacon. Instead, its brightness fluctuates, sometimes over long periods and sometimes more erratically. These variations are tied to its unstable outer layers, which expand and contract, and to the enormous plumes of material being thrown off its surface. For astronomers, this creates yet another layer of uncertainty. When you observe the star at one point in time, you might get a very different measurement than you would months or years later. Without extremely long-term monitoring, it is nearly impossible to understand the full pattern of these fluctuations. Even with our most advanced instruments, there are fundamental physical limits to what we can resolve. Telescopes on Earth must contend with the distortion of Earth's atmosphere, which blurs and shifts incoming light. Adaptive optics and space-based observatories, like the Hubble Space Telescope, help overcome these problems. But even then, the sheer distance and complexity of VY Canis Majoris push against the boundaries of what is possible to observe. Infrared telescopes can peer through some of the dust that obscures it, but interpreting that data requires complex models that depend heavily on assumptions that may or may not fully capture the star's chaotic environment. Adding to these difficulties is the fact that hypergiants like VY Canis Majoris are rare. With so few examples to compare it against, astronomers lack a strong baseline for what to expect. Measuring something is always easier when you have other similar cases to reference. But in this case, each red hypergiant seems to behave differently, and VY Canis Majoris is perhaps the most extreme. It defies easy categorization, leaving scientists with little to no precedent for interpreting their findings. What all of this means is that every piece of data we gather about VY Canis Majoris comes with enormous margins of error. Its radius might be 1,420 times that of the Sun, or it might be closer to 1,800. Its luminosity might be 250,000 times brighter than the Sun, or perhaps significantly less. Even its exact mass is uncertain, with estimates ranging from 17 to 25 times that of the Sun. Each of these numbers matters because they influence predictions about its future. For example, its eventual supernova depends heavily on its mass and structure, and small differences can lead to very different outcomes. In the end, studying VY Canis Majoris is like trying to sketch the outline of a storm while standing inside the storm itself. It is not neat, it is not simple, and it often refuses to conform to expectations. But in that very challenge lies the allure. Each new observation, each refinement of its size, brightness or structure, brings astronomers a little closer to understanding one of the most colossal and mysterious stars in the galaxy. It is precisely because it is so difficult to study that it holds such importance. By pushing the limits of our ability to measure and observe, VY Canis Majoris is forcing us to expand not only our technology, but also our imagination about what stars can be. The true size of VY Canis Majoris has been one of the most hotly debated topics in modern astronomy, and it continues to puzzle researchers to this day. For years, scientists believed that this star was so large that if it were placed at the center of our solar system, its outer layers would extend beyond the orbit of Saturn, possibly even reaching Uranus. Early estimates suggested radii in excess of 2,000 times that of the Sun, making it not just one of the largest stars, but perhaps the largest ever discovered. However, as technology improved and more sophisticated instruments were trained on this stellar giant, astronomers began to realize that the story wasn't so straightforward. Different methods of measurement yielded widely differing results, and even today, no consensus exists on its exact radius. This uncertainty has made VY Canis Majoris not only fascinating, but also controversial, as it exposes the limits of current stellar models and raises questions about whether stars can truly grow to such immense proportions. Part of the difficulty lies in the very nature of VY Canis Majoris itself. Unlike stable stars such as our Sun, whose edges are clearly defined, VY Canis Majoris has an extended, turbulent atmosphere that blurs the boundary between the star's surface and its surrounding environment. The star is undergoing intense mass loss, constantly throwing off material into space, which creates clouds of gas and dust around it. These layers scatter light in complex ways, making it extremely difficult to tell where the star itself ends and its ejected material begins. Depending on which wavelength of light astronomers use to observe it, the measured size can vary dramatically. In visible light, its size can appear immense, while in infrared, where dust and gas are more transparent, it may look smaller. Thus, when different research teams publish their measurements, they sometimes arrive at drastically different values, all technically correct depending on the observational method, but leaving no single true answer. This ambiguity highlights one of the deeper mysteries of stellar physics. What exactly defines the surface of a star like VY Canis Majoris? For ordinary stars, astronomers use the photosphere, the region from which most of the light escapes, as the boundary. But in the case of red hypergiants with thick, dynamic outer layers, the photosphere itself becomes distorted, shifting inwards and outwards depending on the wavelength and the star's activity at any given time. The star's extreme variability further complicates matters, since it is not static but constantly changing in brightness and radius. Observations taken a decade apart may not be directly comparable, as the star could have expanded or contracted significantly during that time. This fluid nature challenges the idea of treating its radius as a fixed number and forces astronomers to think of its size as more of a range rather than a definitive figure. Beyond the observational difficulties, these conflicting measurements also raise questions about the limits of stellar structure theory. If VY Canis Majoris were truly as large as early estimates suggested, more than 2,000 solar radii, then its outer layers would be only loosely bound by gravity, teetering on the edge of instability. Some astronomers argue that it's physically impossible for a star to sustain such a massive radius without collapsing or shedding its atmosphere at a catastrophic rate. Others counter that hypergiants like VY Canis Majoris exist in such extreme conditions that conventional models may not apply, and new physics might be needed to fully explain their behavior. This debate isn't just academic curiosity, it directly affects our understanding of how the most massive stars evolve, how they die, and what kinds of supernova they produce. If VY Canis Majoris defies the standard models, it could mean our theories about stellar evolution need significant revision. Even with the most advanced telescopes available today, the star continues to resist easy categorization. Observations with instruments like the Hubble Space Telescope and the Very Large Telescope, VLT, have provided more detailed images, showing a chaotic environment of arcs, knots, and plumes of material surrounding the star. These structures are the result of uneven and violent mass ejections over the past 1,000 years, and they obscure the star from clear view. When astronomers attempt to measure its size using interferometry, combining the light from multiple telescopes to achieve higher resolution, they still face the problem of disentangling the star's true surface from the glowing material around it. Depending on how the data is modeled, results can swing from several hundred solar radii to well over 1,000, keeping the mystery alive. This uncertainty fuels ongoing debates among scientists. Some suggest that the original claims of VY Canis Majoris, being the largest star in the universe, were overblown, and that with more accurate modern measurements, it may not hold that title anymore. Others argue that even if newer data points to a smaller radius, the fact that it remains one of the most luminous and unstable stars still makes it exceptional. But regardless of where the truth lies, the very fact that its size remains in dispute speaks volumes about the challenges of studying such rare and extreme objects. In a way, VY Canis Majoris forces astronomers to confront the limitations of their tools and theories, reminding us that the universe is not obliged to conform neatly to human expectations. Adding to the intrigue, the question of its size ties directly into its ultimate fate. A larger radius would mean a more diffuse structure, potentially leading to different kinds of supernova explosions than if it were more compact. The uncertainty in size thus translates into uncertainty about what exactly will happen when the star finally dies. Will it go out in a fiery hypernova, leaving behind a black hole? Or will its mass loss strip it enough to produce a less dramatic end? These are not idle questions, but essential pieces in the puzzle of understanding how the heaviest elements in the universe are created and dispersed. The mystery of VY Canis Majoris' size is more than just a numbers game. It is a mirror reflecting the broader struggle of astronomy, to measure and understand phenomena so far beyond our everyday experience that even defining them becomes a challenge. Each new study, whether it supports a larger or smaller measurement, adds another piece to the puzzle, but the picture remains incomplete. This ongoing uncertainty keeps the star at the center of scientific curiosity, ensuring that it continues to inspire not just debates among experts, but also a sense of wonder in anyone who contemplates its unimaginable scale. The question of how big VY Canis Majoris truly is may not have a simple answer, but in chasing that answer, humanity gains deeper insights into the cosmos itself. VY Canis Majoris is not just a spectacle in the sky. It is a critical subject of study in astronomy because of what it represents. One of the most extreme stages in the life cycle of a massive star. Its role in astronomy extends far beyond its sheer size and brightness. By studying a star like VY Canis Majoris, scientists gain access to a living laboratory where the principles of stellar physics can be tested at scales rarely observed in our galaxy. It serves as a kind of cosmic experiment, unfolding in real time, and each observation of it adds a piece to the puzzle of how massive stars live and die. Without objects like this, our models of stellar evolution would remain incomplete and theoretical, missing the confirmation of what actually happens when a star reaches the upper boundaries of size and luminosity. One of the most important contributions of VY Canis Majoris to astronomy is in clarifying the limits of stellar mass and stability. Stars like our Sun are relatively easy to model because they are stable and well-behaved. But hypergiants like VY Canis Majoris push those models to their breaking point. Its immense radius, which at times has been estimated to extend nearly to the orbit of Saturn, raises profound questions about how such a star can physically hold itself together against the relentless pull of gravity and the equally fierce outward push of radiation. The existence of this star tests the very physics of hydrostatic equilibrium, the balance that keeps stars stable. If astronomers can understand how VY Canis Majoris maintains this balance despite its diffuse outer layers and massive stellar winds, they can refine models of how stars behave at these extremes. Another key role the star plays is in illuminating the process of stellar mass loss. Massive stars do not simply shrink quietly into white dwarfs like smaller stars. They lose vast amounts of material into the surrounding space. VY Canis Majoris is shedding its outer layers at such an extraordinary rate that it has created a vast nebula of gas and dust surrounding it. Studying this mass loss not only helps astronomers understand the star's current state, but also reveals how massive stars contribute to galactic ecosystems. The material expelled by VY Canis Majoris enriches the interstellar medium with heavier elements, oxygen, carbon, silicon, that become the building blocks of future stars, planets, and even life. In this way, the study of VY Canis Majoris connects the fate of an individual star to the broader cycle of cosmic recycling. The star also helps astronomers refine their understanding of supernova progenitors. VY Canis Majoris is expected to end its life in a violent supernova explosion, and by examining its current properties, scientists can better predict the warning signs leading up to such an event. For example, the rate of mass loss, the irregular pulsations of its atmosphere, and its rapidly changing brightness are all clues to the final collapse. If astronomers can catalogue these behaviours in VY Canis Majoris and then compare them to supernova events observed elsewhere, they will be able to link pre-supernova conditions with post-explosion observations. This makes VY Canis Majoris an invaluable reference point in the study of stellar deaths, which in turn helps refine models of how elements are distributed across galaxies when massive stars explode. Furthermore, VY Canis Majoris provides insights into the challenges of stellar measurement itself. Its immense size and the thick layers of gas and dust it has expelled make it notoriously difficult to measure accurately. Different instruments and techniques have yielded widely varying estimates of its diameter, mass, and luminosity. By wrestling with these challenges, astronomers improve their observational techniques and refine tools like interferometry and spectroscopy, which can then be applied to other distant stars. The star becomes not just an object of study, but also a testing ground for methods that expand the overall capabilities of astronomy. In this sense, it serves as both a subject and a teacher, forcing scientists to innovate in order to understand it. Equally important is the role of VY Canis Majoris in public engagement with astronomy. Massive, unusual stars like this one capture the imagination in a way that smaller, less exotic stars rarely do. When people learn that a single star can be larger than the orbit of Jupiter, or even comparable in size to the orbit of Saturn, it sparks a sense of wonder and curiosity about the universe. This engagement helps inspire future generations of astronomers, engineers, and scientists. In this indirect but vital way, the study of VY Canis Majoris supports the growth of astronomy by feeding human curiosity and motivating the pursuit of knowledge. Additionally, VY Canis Majoris is a reminder that our galaxy is filled with extremes that often challenge long-held assumptions. For decades, astronomers believed stars could not grow beyond certain sizes without collapsing under their own weight. Yet here is a star that stretches those assumptions to their limit. Its very existence forces the scientific community to revisit and refine what is possible in stellar evolution. Each anomaly it presents, whether it is the discrepancies in size measurements, the irregularities in its light curve, or the dynamics of its mass loss, represents not a failure of science, but an opportunity to deepen understanding. In essence, VY Canis Majoris plays a crucial role in bridging theory with observation. It is one thing to propose equations and models that describe how stars should behave. It is quite another to confront a real star that seems to bend or even break those rules. In confronting such stars, astronomers are forced to re-examine, adapt, and sometimes completely revise their theories. This iterative process is at the heart of science, and stars like VY Canis Majoris are the catalysts that keep it alive and dynamic. Ultimately, the role of VY Canis Majoris in astronomy is multifaceted. It is a testing ground for stellar physics, a laboratory for mass loss and nebula formation, a clue to the nature of supernova progenitors, a challenge for observational astronomy, and a beacon for inspiring human curiosity. Through it, astronomers are not only learning about one star, but also about the universe as a whole, how stars shape galaxies, how elements are forged, and how cosmic cycles of birth and death sustain the evolution of everything we see. In this way, VY Canis Majoris is not just an astronomical curiosity. It is a keystone in the effort to understand the life and death of the most massive stars, and by extension, the very processes that make the universe habitable and alive with complexity. When discussing VY Canis Majoris, it's almost impossible not to place it into a cosmic neighborhood, a community of other colossal stars that challenge our imagination about size, brightness, and destiny. While each star is unique, comparing VY Canis Majoris with others like Betelgeuse, UY Scuti, Antares, and Mu Cephei not only puts its staggering dimensions into perspective, but also paints a larger picture of what extreme stellar evolution looks like across our galaxy. Each of these stars tells a different part of the same story: how massive stars live, age, and eventually die in spectacular fashion. By seeing how they stand against one another, we gain a better appreciation for the diversity of stellar giants. Take Betelgeuse, perhaps the most famous red supergiant in the sky. Located in the constellation Orion, Betelgeuse has fascinated humanity for centuries, shining as a bright reddish point visible to the naked eye. While Betelgeuse is enormous by most standards, roughly 700 to 1,000 times the diameter of the Sun, it is still significantly smaller than VY Canis Majoris in terms of sheer radius. If placed at the center of our solar system, Betelgeuse's surface would extend past the orbit of Mars, maybe even grazing Jupiter, depending on which measurement you use. But VY Canis Majoris dwarfs it, reaching nearly to Saturn's orbit or beyond. The difference is like comparing a mountain to a continent. Both are immense, but one completely dominates the landscape. What makes Betelgeuse stand out, though, is its closeness to Earth, about 640 light-years away, which allows astronomers to study it in remarkable detail. Its famous dimming event in late 2019 and early 2020 caught worldwide attention, with people speculating whether it was about to go supernova. In truth, Betelgeuse probably has tens of thousands, maybe even hundreds of thousands of years left before it explodes. But the excitement highlighted how closely humanity watches its stellar neighbors. In comparison, VY Canis Majoris is far more distant, about 3,800 to 4,000 light-years away, meaning we cannot observe the same fine details as easily. But in terms of sheer physical presence, VY Canis Majoris makes Betelgeuse look like a modest star. Then there is UY Scuti, a red supergiant located in the constellation Scutum, which for some time has held the record as the largest known star by radius. UY Scuti is estimated to be around 1,700 times the radius of the Sun, which slightly edges out some of the upper estimates for VY Canis Majoris. However, the debate comes down to methodology. Measuring the size of such stars is notoriously difficult because their outer atmospheres are not well defined. Both UY Scuti and VY Canis Majoris have extended, tenuous layers of gas and dust that blur the boundary between star and surrounding nebula. In other words, where does the star actually end? This question complicates the ranking of largest stars. Some astronomers argue VY Canis Majoris is larger, while others lean toward UY Scuti, depending on where you draw the line. But regardless of which one comes out ahead, both are in a class of stellar titans that make even Betelgeuse seem small. Interestingly, UY Scuti is much brighter than VY Canis Majoris, shining as a luminous supergiant rather than a dim hypergiant. This difference in brightness underscores the fact that size alone does not determine a star's overall power. VY Canis Majoris, though massive and extended, has a relatively cool surface temperature and spends much of its energy driving stellar winds and mass loss rather than dazzling with visible light. Another comparison worth making is with Antares, the red supergiant in the constellation Scorpius. Known as the heart of the Scorpion, Antares is a bright, easily spotted star in summer skies. It is roughly 700 times the radius of the Sun, placing it in the same ballpark as Betelgeuse. If Antares were located in the solar system, its surface would likely extend somewhere between Mars and Jupiter. Again, a staggering size, but still only a fraction of what VY Canis Majoris encompasses. What makes Antares especially interesting is its pairing with a much smaller, hotter blue companion star, Antares B. This binary system provides astronomers with a natural laboratory to study mass transfer and interactions between stars of different temperatures and evolutionary stages. In contrast, VY Canis Majoris appears to be a solitary giant with no known stellar companions. That isolation may play a role in how it evolves, without another star pulling at its outer layers or exchanging material. VY Canis Majoris has been free to shed its mass into the surrounding nebula largely unhindered, shaping a unique evolutionary path. Mu Cephei, sometimes called Herschel's garnet star, is another red supergiant worthy of mention. It is around 1,000 to 1,500 times the radius of the Sun and shines with a deep red hue that makes it stand out in the night sky. Though not as large as VY Canis Majoris, Mu Cephei exemplifies the red supergiant stage at its most striking and colourful. Its name, garnet, reflects its gem-like appearance through telescopes, making it a favourite among amateur astronomers. Like VY Canis Majoris, Mu Cephei is believed to be nearing the end of its life and will likely go supernova within a few million years. Both stars illustrate the extremes of stellar aging, though VY Canis Majoris, by virtue of its larger size and mass loss, may follow a slightly more chaotic path toward its final explosion. When comparing these stellar giants, it is important to consider not just size, but also luminosity, distance, temperature, and evolutionary status. VY Canis Majoris is not the brightest or most massive star, but it is among the most inflated. Its surface has expanded to staggering distances due to its late stage of evolution, where internal processes push its outer layers outward even as gravity struggles to hold them in. UY Scuti may rival it in size. Betelgeuse and Antares may be more familiar to the general public due to their brightness and position in the sky, and Mu Cephei may win awards for beauty, but VY Canis Majoris occupies a unique place as a representative of the hypergiant class. Hypergiants are rare, far rarer than red supergiants, and VY Canis Majoris is one of the few we can study in such detail. There's also the question of what happens when these stars end their lives. Betelgeuse will almost certainly explode as a Type II supernova, briefly shining brighter than the full moon in Earth's skies. Antares will likely follow a similar fate. UY Scuti's destiny remains debated, but it too may end in a core collapse supernova. For VY Canis Majoris, the future might be even more dramatic. Some models suggest it could collapse into a black hole directly after shedding much of its outer mass, bypassing a bright supernova altogether. Others suggest a supernova is inevitable, and given its sheer size, the explosion could be one of the most energetic in the galaxy. Comparing these outcomes side by side reveals the range of possibilities for massive stars and the uncertainty that still clouds our predictions. Another fascinating aspect lies in cultural impact. Betelgeuse, Antares, and Mu Cephei have all been visible to the naked eye for millennia, inspiring myths and names across civilizations. VY Canis Majoris, on the other hand, remained obscure until the modern era, because of its distance and relative faintness. It was only through telescopes and advanced instruments that we realized just how staggering its size is. In that sense, VY Canis Majoris represents the hidden giants of the cosmos, objects so immense they defy comprehension, yet invisible to casual stargazing. The comparison between VY Canis Majoris and its stellar neighbors isn't about crowning a single largest star, but rather about highlighting how diverse and extreme stars can become. Each of these giants occupies a different corner of the map of stellar evolution. Together, they remind us that the universe produces objects far beyond the scale of our everyday lives. When we look at Betelgeuse, UY Scuti, Antares, Muchefe, and VY Canis Majoris side by side, we see not just numbers and statistics, but a living story of birth, growth, decline, and eventual death written in fire and light. It is a story that continues to unfold, and each new observation reshapes how we rank, compare, and understand these stellar behemoths. VY Canis Majoris is not just an isolated behemoth in the cosmos. Its sheer size, energy output, and ferocious winds make it an active sculptor of its surrounding environment. Unlike ordinary stars that live relatively quiet lives, this red hypergiant's influence extends far beyond its own atmosphere. Its outer layers are constantly being blown off in colossal eruptions and through continuous streams of stellar winds, carrying with them the raw materials for future generations of stars and planets. These massive outflows form intricate clouds of gas and dust around the star, creating nebulae that shine with reflected light and infrared radiation. The shapes of these nebulae are far from uniform. Instead, they appear fragmented, clumpy, and chaotic, resembling vast cosmic sculptures carved by unseen hands. This is the direct fingerprint of VY Canis Majoris on its corner of the galaxy, an ongoing transformation that tells us about both the star's turbulent life and the processes that recycle stellar material into the broader interstellar medium. The impact of its stellar winds is especially significant because they carry away not only mass, but also momentum and energy. When these winds collide with surrounding gas, they compress it, forming dense pockets that can later collapse under gravity to form new stars. In this sense, VY Canis Majoris is both a destroyer and a creator. It destabilizes its own atmosphere and hurls matter into the void, but that very process enriches the galactic neighborhood with heavy elements like carbon, oxygen, silicon, and eventually iron when it explodes as a supernova. These elements are essential building blocks for rocky planets, for atmospheres, and even for life itself. Without hypergiants and other massive stars recycling their material into the cosmos, the universe would remain chemically primitive, filled only with hydrogen and helium. Thus, the fierce winds of VY Canis Majoris are a crucial step in cosmic alchemy, seeding space with the ingredients of complexity. One of the striking aspects of its influence is the scale of its nebulae. The expelled gas around VY Canis Majoris stretches many thousands of astronomical units into space, dwarfing the scale of our entire solar system. The nebula is not a smooth shell, but rather a chaotic expanse of arcs, knots, and filaments, evidence of irregular mass ejections. Astronomers suspect that these asymmetrical shapes are caused by localized convective events in the star's outer layers, or perhaps even giant magnetic fields disrupting the flow of plasma. Each eruption reshapes the surrounding nebula, layering new structures on top of old ones, like rings in a tree trunk. But here, the rings are cosmic clouds drifting away into space. Observations with instruments like the Hubble Space Telescope and the Very Large Telescope have revealed the extraordinary complexity of these ejecta, turning VY Canis Majoris into a kind of natural laboratory for studying the chaotic dynamics of late-stage stellar mass loss. Another profound way the star impacts its surroundings is through radiation. As one of the most luminous red hypergiants, VY Canis Majoris bathes its environment in powerful light across the electromagnetic spectrum. Ultraviolet radiation ionizes the gas, causing it to glow, while infrared emissions heat the dust grains in the nebula. This radiation pressure also helps push the material outward, working hand in hand with the stellar winds to shape the nebula. Over time, the combination of radiation and winds clears out cavities in the surrounding medium, carving bubbles of emptiness in which later supernova shockwaves can travel with less resistance. This preconditioning of the interstellar environment ensures that when VY Canis Majoris finally explodes, the blast will propagate differently than it would in an unperturbed region of space. The shockwave will collide with pre-shaped shells and filaments, lighting them up like fireworks and creating dazzling supernova remnants that astronomers will study for centuries to come. The sheer variability of the star's mass loss also adds to the complexity of its surroundings. Unlike stars that lose material in a steady flow, VY Canis Majoris seems to undergo episodic events where enormous amounts of matter are suddenly ejected. Some astronomers describe these outbursts as mini eruptions, not unlike scaled-down versions of a supernova. Each episode leaves behind a distinctive signature in the nebula, with arcs and knots that can be traced back to different points in the star's recent history. By studying these structures, astronomers essentially piece together a timeline of the star's last few thousand years, a window into its unstable decline. These nebulae become more than just pretty shapes in space. They are archives of stellar instability, cosmic journals that record every outburst and convulsion of the star's life. But the impact of VY Canis Majoris is not limited to shaping nebulae. Its mass loss contributes directly to the interstellar medium, the vast reservoir of gas and dust that pervades the galaxy. Over millions of years, the contributions of massive stars like this one enrich the galaxy with heavier elements, driving a slow but steady evolution in the chemistry of the cosmos. Future generations of stars will be born from this enriched medium, and some of them will have planetary systems capable of sustaining life. In this way, VY Canis Majoris plays a role in a much larger story, the cosmic cycle of birth, death, and rebirth that defines our universe. It may be a single star in a distant constellation, but the materials it has shed will eventually become part of countless new worlds, some perhaps with oceans, mountains, and even life. On a more immediate scale, its winds and eruptions also alter the dynamics of nearby interstellar clouds. Dense molecular clouds, the cradles of new stars, are particularly sensitive to the effects of stellar winds. When a massive star, like VY Canis Majoris, blows out huge amounts of gas, it can compress nearby clouds, nudging them into collapse and triggering the formation of new stars. At the same time, the turbulence injected into the region by these winds can disrupt clouds and prevent collapse in other areas. Thus, the star acts as both a catalyst and an obstacle to star formation, a dual role that underscores the complex relationship between massive stars and their environments. Astronomers studying star-forming regions often look to examples like VY Canis Majoris to understand how feedback from giant stars shapes the galactic ecosystem. There's also a looming question about what will happen when VY Canis Majoris finally explodes. A supernova of this magnitude will send shockwaves through the surrounding nebula, colliding with the shells of material already ejected. This interaction will generate enormous amounts of radiation, accelerating particles to near light speeds and producing brilliant emissions across the electromagnetic spectrum. The resulting supernova remnant will likely be one of the most spectacular in the Milky Way, a glowing web of filaments expanding outward for tens of thousands of years. The energy injected into the region will reshape it entirely, sweeping up gas and dust, compressing some areas while clearing out others, and leaving behind a neutron star, or perhaps even a black hole at the center. The long-term impact on the surrounding interstellar medium will be immense, ensuring that the influence of VY Canis Majoris will continue long after the star itself is gone. Even at its current stage, the surrounding nebula offers astronomers a unique window into the physics of mass loss and feedback. By mapping the motion of gas in the nebula, researchers can estimate the rate at which the star is shedding material and reconstruct the history of its mass ejections. By studying the chemical composition of the expelled material, they can see which layers of the star have been exposed and which nuclear processes are at work deep inside. And by examining the shapes of the nebular arcs and filaments, they can learn about the turbulent forces shaping the outflows. Every detail in the environment around VY Canis Majoris tells a story, and piecing those stories together helps astronomers understand not only this particular star, but also the broader population of massive stars in our galaxy and beyond. In the end, the influence of VY Canis Majoris on its surroundings is a vivid reminder that stars are not isolated points of light, but dynamic engines of transformation. They mold the space around them, enriching it, sculpting it, and preparing it for the next stages of cosmic evolution. The nebulae surrounding VY Canis Majoris are more than just byproducts of a dying giant. They are monuments to the processes that keep the galaxy alive and evolving. When we look at these vast clouds of gas and dust, we are witnessing the echoes of a star's struggles against its own instability, and at the same time seeing the seeds of new beginnings. The legacy of VY Canis Majoris will be written not just in its eventual supernova, but also in the countless stars and planets that may one day emerge from the material it has already shed. It is both an ending and a beginning, a star that through its turbulent life continues to shape the universe around it in ways that will be felt for millions of years to come. If we were to take VY Canis Majoris, this red hypergiant star of unimaginable proportions, and place it right where our Sun currently resides, the scenario would be nothing short of apocalyptic for our solar system. To even begin grasping this hypothetical situation, one has to imagine that the very boundaries of our planetary neighborhood would be obliterated and reshaped. The Sun, modest in comparison though vital to us, has a radius of about 695,000 kilometers. VY Canis Majoris, at its most widely accepted estimates, can swell to between 1,500 and 2,000 times that size. Its radius could extend out far beyond the orbit of Jupiter. That means if it were at the center of our solar system, Earth, Mars, the asteroid belt, and Jupiter itself would all exist within the outer layers of this star. Their orbits would no longer be around the star. They would be inside it, engulfed and vaporized in its fiery plasma. The first consequence would be the instant destruction of the inner planets. Mercury, Venus, Earth, and Mars would be completely consumed, melted down into their constituent atoms in an environment so hot and unstable that even iron would evaporate. The asteroid belt, too, would not stand a chance. It would be swallowed up inside the convective outer atmosphere of VY Canis Majoris. For Earth, there would be no trace left at all, not even a rocky husk. The crust, mantle, and core would disintegrate into ionized plasma, merging with the swirling gases of the star. This is the scale of destruction we are talking about when imagining such a replacement. The outer planets, Jupiter, Saturn, Uranus, and Neptune, would present a slightly more complex story. Depending on the maximum size estimates, Jupiter would either be completely inside the star or right at its boundary. If within, it too would dissolve in the crushing heat and turbulence of the hypergiant's outer layers. If only at the fringe, the star's powerful stellar winds and radiation would strip it of its atmosphere rapidly, leaving no planet recognizable as we know it. Saturn and Uranus might briefly survive in some distorted orbit near the edge of this cosmic monster, but survival in the long term would be impossible. The heat and radiation would tear apart their gaseous envelopes, leaving behind little more than naked cores. Neptune, the farthest of the classical planets, would likely be the only one outside of the star's body, yet even it would not remain unaffected. The stellar winds from VY Canis Majoris are fierce, thousands of times stronger than the Sun's solar wind. They would bombard Neptune with streams of charged particles, stripping away its atmosphere and destabilizing its orbit. The Kuiper belt and Oort cloud, which house icy bodies and potential comets, would also be subjected to this star's wrath. The Kuiper belt objects would be rapidly heated, sublimating their frozen ices into vapor, leaving behind debris that would either fall into the massive stellar winds or be flung outward into interstellar space. The Oort cloud, being much farther, might survive in a more literal sense, but its structure would be drastically disturbed. The gravitational field of VY Canis Majoris is far stronger than that of the Sun, and it would scatter these distant icy bodies, sending some hurtling into interstellar space, and others crashing inward where they would be vaporized near the hypergiant. Beyond the physical destruction of planets and icy bodies, one has to consider the sheer radiation output. The Sun emits enough energy to sustain life on Earth comfortably at 1 AU, about 150 million kilometers away. But VY Canis Majoris emits hundreds of thousands of times more energy. Even if Earth were much farther away than it currently is, it would still be fried by the radiation. The habitable zone around such a massive star wouldn't exist in any conventional sense. Life as we know it thrives in stable, relatively mild environments. VY Canis Majoris is the polar opposite of stability. It is turbulent, unstable, and spewing mass into space at a rate millions of times faster than our Sun. There would be no chance for life to exist anywhere nearby. This leads us to consider orbital mechanics. The solar system's planets currently follow stable paths because the Sun's gravitational field dominates the region. Replacing the Sun with VY Canis Majoris would dramatically alter the gravitational balance. The increased mass, combined with its gigantic size, would shift orbital dynamics completely. Any surviving fragments of planets or icy bodies would find their orbits disrupted, possibly being flung into interstellar space or drawn inward to destruction. The solar system, as we know it, would cease to exist, not just physically, but also structurally. The tidy system of planetary orbits we rely on would be destroyed and replaced by chaotic, violent streams of debris interacting with the hypergiant's gravity and winds. Interestingly, even though VY Canis Majoris is a true titan, its enormous size doesn't necessarily make it more gravitationally binding on a per-volume basis. Its density is extremely low, with its outer layers being so diffuse that if you could somehow stand within them, you might not even realize you were inside a star, at least not immediately. The outer atmosphere is tenuous and stretched thin over an immense volume. But the core of the star is where its mass is concentrated, and that core drives the monstrous gravity and energy output that governs its environment. For planets like Neptune or the remnants of Saturn, this means even if they were outside its physical radius, their orbits would become unstable simply due to the change in mass distribution and gravitational dominance. Now let us consider the cosmic consequences of having such a giant in the middle of our neighborhood. A star like VY Canis Majoris has a limited lifespan, far shorter than our Sun's stable 10 billion year run. In just a few 100,000 years, an instant in cosmic time, it would reach the end of its life and go supernova. If placed in our solar system, that explosion would annihilate everything within tens of light years. Not only would the solar system be obliterated, but nearby stars would feel its effects. Radiation, shock waves, and newly forged heavy elements would ripple through space, reshaping the galactic environment. And yet, this hypothetical scenario also offers insight into why studying stars like VY Canis Majoris is important. Imagining it at the center of our solar system allows us to appreciate the fragility of planetary systems and the unique balance that makes life possible on Earth. If our Sun were even slightly different, larger, hotter, or more unstable, Earth might never have developed life at all. The sheer scale of destruction that VY Canis Majoris represents underscores the rare, delicate stability of our own star. In short, if VY Canis Majoris were to replace our Sun, the solar system would not survive in any recognizable form. The inner planets would be destroyed instantly, the outer ones stripped and destabilized, and the distant icy bodies scattered to oblivion. Radiation would sterilize everything, and the gravitational chaos would unravel the system entirely. Eventually, the hypergiant's explosive death would erase whatever remnants were left. It is a stark reminder of the unimaginable scale of the cosmos and the razor-thin line between creation and destruction in the life cycles of stars. VY, Canis Majoris, reminds us of the vastness of the universe, a star so immense it makes our solar system look like a speck of dust. In the grand expanse of the cosmos, we often feel as though our sun, so dominant in our skies and so central to life on Earth, must be among the greatest of celestial bodies. And yet, when confronted with the enormity of a star like VY Canis Majoris, the illusion of human centrality dissolves. The Sun, powerful and vital as it is, would be utterly dwarfed by this red hypergiant, a stellar behemoth whose scale stretches the imagination to breaking point. Its radius could engulf the orbit of Jupiter. Its volume could fit billions of suns inside. It is not just a star, it is a monument to cosmic power, a reminder that the universe builds structures far beyond the realm of human comprehension. To gaze upon VY Canis Majoris is to be reminded that the cosmos is not constructed with our perspective in mind. The vastness is not scaled for human comfort, nor tailored to the limits of human imagination. Instead, the universe is grand, indifferent, and overwhelmingly vast, populated with wonders that defy our intuition. This star, sitting some 3,900 light-years away in the constellation of Canis Major, is one such wonder. It radiates not only energy and light, but also humility, forcing us to recognize the scale of creation and the smallness of our own position within it. Even in its distance, it compels awe, a beacon of cosmic enormity shimmering across the gulf of space. There is poetry in its very existence. Imagine a star so vast that if it replaced our Sun, it would swallow not only Earth, but worlds beyond. Saturn, Uranus, Neptune, all would be adrift within its fiery boundaries. Our entire solar system would be nothing more than a bright ember flickering inside its photosphere. And yet, despite its grandeur, this star is not eternal. Like all things in the cosmos, it is subject to the relentless march of time. One day, it will collapse in on itself, unleashing its final breath as a supernova, or perhaps something even more catastrophic, and in that moment, it will light up the galaxy with a brilliance that eclipses billions of lesser suns. This too carries a lesson. Even the mightiest of stars, titans whose radii stretch across unimaginable distances, are impermanent. They are born, they blaze, they fade. Their stories unfold over millions of years, but in cosmic terms, their lifespans are short, like the flare of a match against the endless night. For VY Canis Majoris, its time is already running out. It is in its twilight, its final act, casting off layers of material into the cosmos, sculpting nebulae and seeding space with the raw ingredients for future worlds. Its eventual death will be as spectacular as its life, a cosmic fireworks display that will echo across the Milky Way for millennia. And perhaps that is where the deepest awe resides, not just in the size, not just in the scale, but in the cycle. VY Canis Majoris, for all its incomprehensible enormity, is part of a greater rhythm. It was born from a cloud of gas and dust, and it will return its elements back to that interstellar sea. The oxygen in our lungs, the carbon in our cells, the iron in our blood, all were forged in stars, not unlike this one, long before Earth existed. The hypergiants are alchemists of the universe, building the elements that make life possible. And when they die, they scatter these treasures across the cosmos, planting the seeds of new suns, new planets, and new stories. VY Canis Majoris is not only a giant, it is a creator, a reminder that death in the universe is never truly an end, but a transformation. From Earth, we can only look upon it as a faint, flickering point of light, its enormity veiled by distance. Our eyes cannot perceive the true scale. Our minds struggle to hold the numbers. But with telescopes and mathematics, we peel back the curtain and glimpse the extraordinary reality that a single star can be larger than the space we call home, that its very presence reshapes the environment around it, that it humbles the grandiosity of our human achievements with its sheer existence. It is a star that forces us to measure our place in the cosmos not in miles or meters, but in humility. There is a haunting beauty in knowing such things exist, so far from us and yet so real. They burn, they live, they die, indifferent to whether or not conscious beings witness them. And yet, we do witness them. We point our telescopes at the night sky. We record the faintest signals. We study the data. And in doing so, we bridge the impossible gulf between ourselves and the stars. VY Canis Majoris does not know that it has inspired awe in human hearts. It does not know that its name is spoken in classrooms, written in books, whispered in documentaries, and dreamed about by stargazers. It simply is, and perhaps that is enough. Its existence alone is the poetry. So when we think of VY Canis Majoris, we should not only think of its size, we should think of the humility it demands, the wonder it sparks, and the cosmic truth it represents. That we are small, yes, but we are capable of awe. We are capable of looking up into the night, of measuring and imagining, of recognizing that the universe is greater than ourselves. And in that recognition, there is beauty. For to be small in a vast universe is not to be meaningless. It is to be part of something larger than we can ever comprehend. VY Canis Majoris reminds us of the vastness of the universe, a star so immense it makes our solar system look like a speck of dust. But more than that, it reminds us of the fleeting, fragile, and precious nature of existence. It is a star nearing the end of its life, yet it glows with a grandeur that will echo long after it is gone. One day, it will collapse, and from its death will come new beginnings, clouds of gas, new stars, new worlds, perhaps even new forms of life. And so, in the life and death of this single star, we glimpse the eternal cycle of the cosmos. In the end, the awe is not only in its immensity, but in the lesson it imparts, that everything, no matter how grand, is part of a greater story. Our sun, our earth, our species, all are chapters in that same cosmic narrative. And as we gaze up at VY Canis Majoris, we are reminded not only of how small we are, but of how miraculous it is that we exist at all to witness it. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.